Assalamualaikum and hi to all. So this is part 4 video of Exergy chapter 1. So in this video I'm going to explain the Exergy change of a system. Exergy change of a system. Exergy change of a system. Exergy change delta X. So we know we have two kind of system, which is closed system and also open system. Now in Exergy, the closed system is called Exergy of a fixed mass, which is referring to the non-flow closed system. So as we all know, in the closed system, there is no mass in and mass out, but there is an energy in and out, and the mass is constant. So there is another system which is an open system. In Exergy, it's called Exergy of a flow stream, and open system Exergy. So this is one example of the open system. As you can see here, we have two mass flow rate in and one mass flow rate out. And from these two concept or system, which is closed and open system, we use the reference equation, which is the energy balance equation. From the energy balance equation, E in minus E out is the net energy transfer, and delta E system is the energy change of a system. Exergy of a fixed mass non-flow closed system exergy. So this is from the energy balance equation, which is E in minus E out is the net energy, and also delta E system is the energy change of the system. So we expand the system. And we consider three energy coming from three source, which is the heat, work done, and also coming from mass flow rate in and out. So now we further look into the energy change for the non-flow system, which is a closed system. So this is a closed system. There is no mass flow rate in and out. So for this case, we can remove the mass flow rate in and mass flow rate out from the energy balance equation. And then we look into the energy changes, which is a delta E system. It is equal to the summation of internal energy plus the kinetic energy and also potential energy. Delta meaning changes. So in this case, we look into the kinetic and potential energy of the system. So however, for the kinetic and potential energy, which is coming from the microscopic energy, so let's say the system have a velocity, then we should consider the kinetic energy. And let's say also the system has different elevation or at certain height. So we also need to consider potential energy. But in normal thermodynamic system or analysis, we will ignore both of these because normally in the system does not have any changes in velocity, microscopic velocity, and also there is no changes in the elevation. Now there is only an internal energy of the system. So internal energy coming from the molecular interaction. So the unit or the symbol we use U, and it's come from actually sensible energy, one from sensible energy, which is the molecules kinetic energy from the vibration and the motion of the molecule inside of the system. And another one is the latent energy, which is the binding force of the molecule. So both of these systems you can change by heat. It can be changed by heat. However, in second law of thermodynamics, not 100% of heat will produce work. So from this case, we know that we don't know what is the maximum work potential of the internal energy since we have also losses. So now let's look at the second slide. Exergy of a fixed mass non-flow closed system exergy. So as we all know, heat from the second law of thermodynamics state that not 100% of heat will produce work. And from this statement, we know that the work potential of the internal energy should not be more than the internal energy itself. So consider a system, piston cylinder system, and then there is a water trap inside it. Then we give heat to the water, let's say 100 kilojoule of heat, and this is the internal energy will absorb the 100 kilojoule of this energy. And from the sensible energy, the molecule will vibrate and rotate and will increase the temperature from 35 degrees Celsius, which is the atmospheric pressure, to atmospheric temperature to 100 degrees Celsius by using the 100 kilojoule of heat. And then from this 100 kilojoule of heat, the latent energy, which is some of the molecule break, since we already know that liquid water will change phase at 100 degrees Celsius. So from this 100 kilojoule of energy, so from the breakup of the molecular binding, so 70 kilojoule of it turn out to be steam, and then there is a heat release, which is the 30 kilojoule, and from this 70 kilojoule will generate network output. So this is the best case of the system. So in this case, the maximum work potential of internal energy is equal to exergy of the system. Okay, so let's consider a stationary closed system, something like this, a piston cylinder device again, and then we have the condition inside of it is at certain pressure and temperature P and T, and it will move to the certain at not certain at atmospheric pressure equilibrium, which is P naught and T naught, and it will generate useful work. So the initial state is a specified state, and also this is a reversible process, and we assume that the final state is the environment state. So this is the exergy definition. Exergy of a fixed mass, non-flow closed system exergy. So this is a closed system which has no mass in and out. So from this system, we know this is the exergy equation. Okay, to further understand how we get this equation, if you want to know the detail of this equation, you should refer the textbook of Cheng. So however, in this slide, we already simplified it and something like this. So the U naught, P naught, V naught, T naught, and S naught is the condition at the dead state, internal energy, volume, pressure, temperature of the dead state. So from this equation, which is the exergy of a fixed mass. And then we also should consider the kinetic and potential energy in the exergy of the system. And per unit mass is shown as in this equation. So you should take note that in exergy equation, we also consider internal energy and also kinetic and potential energy. Same with the per unit mass. So for non-flow exergy change, uh, this one is the exergy value. The top one is the exergy value. However, this one is exergy change, which is the exergy from state 2, from state 1 to state 2. That is the non-flow exergy change, or the exergy change. So from this, you can see that we have the exergy of a state 2 minus the exergy of state 1. And this is the expansion of the equation based on the exergy of a fixed mass equation. And in normal cases, we neglect the kinetic and also potential energy. So the exergy change for the non-flow system will reduce to this equation, as you can see in this slide. Exergy of a flow stream. Flow stream exergy, which is for the open system, control volume. Okay, we already looked into the closed system and we already developed the equation of the closed system. Now we look into the open system. Okay, first we look into the fundamental equation, which is the energy balance equation. And here we should consider all of the equation, which is Q in, Q out, W net in, W in and W out, and also E mass in and mass out. First, we look into the energy change of system for the non-flow system. So here is a closed system. Delta E system is equal to the summation of the internal energy, potential energy, and also the kinetic energy. So in this case, we only consider the internal energy, delta U. However, in the energy change for flow system or the open system, we have the work done from the mass flow rate, which is can be converted into work flow is equal to PV. before entering and entering. So we need to consider the mass in and out. So in this case, we should include the energy change of the system from equal to delta U plus the V delta P plus kinetic energy and also potential energy. Here is the V delta P is the flow energy from the flow rate. So as we all know, the delta U plus V delta P is equal to delta H, which is the enthalpy of the system. Exergy of a flow stream exergy. So this is the energy balance equation, and then we look into the energy change of the system, and this is one type of the system. And from the as we already developed in the previous slide, so the energy changes of the system consists of the delta U plus V delta P plus KE plus delta PE, which is the in kinetic and potential energy, and also flow energy from the mass flow rate. So the flow energy we can, which is from the workflow equal to PV, we can convert it into exergy type, which is X flow equal to P minus P naught V. So we know that exergy of a flow system, which is open system, is equal to the exergy of a closed system plus this exergy of the flow from the flowing fluid of the PV. So this is the additional equation that we need to put into the exergy equation, and the expansion is in the red rectangular, dotted rectangular. So from exergy flow system, we should add the P minus P naught V. This is the difference between the exergy of non-flow system and also flow system. So exergy of a flow stream, then as you can see, this is the equation of the exergy of a flow stream per unit mass, and also this is the exergy uh, with the times the mass. So from here you can see that for the case of closed system or non-flow system, here is the internal energy. However, in the flow system or open system, here is the enthalpy. How do we get this? Is from this equation where you already know in previous thermodynamics, H equal in thermodynamic 1, H equal to U plus PV. From these three equation, U minus U naught plus P naught V minus V naught plus P minus P naught times V, we can convert it into enthalpy. H minus H naught, and so flow exergy change. This is the uh, exergy equation for the flow exergy change from state 1 to state 2. And if we neglect the kinetic and potential energy, which is highlighted in the red dotted rectangular, then we can get this exergy flow change of equation. So exergy balance equation, energy balance equation. So this is the energy balance equation, which is come from heat, work, and mass. And then the maximum energy potential from this energy balance equation is the exergy balance equation. So as you can see here, X in minus X out, which is almost similar to the energy balance equation. And then it should have also heat energy in and also work, and heat energy in and out, also work energy in and out, and also mass flow rate in and mass flow rate out. Minus, we have one question mark there, and then equal to delta X system, which is the uh, exergy balance equation. So here you can see that delta E system, which is the energy balance equation, changes of the system almost similar to the exergy of the system. And for the closed system, uh, this is the delta X system for the closed system, which is the exergy changes of the system, and also for the closed system and also for open system, which is, as I mentioned earlier, it's come from heat, work, mass flow rate in and out, and also another one is the losses or the irreversibility. So please take note the difference between the energy balance equation and also exergy balance equation, and also please consider the system, either it is a closed system or it is an open system. And please keep in mind the differences between open system and closed system, where as you can see for the open system, the internal energy and pressure turn out to be the enthalpies. So it can be positive or negative, depend on the individual value of exergy for each state, and also individual flow exergy for each state is always positive. However, the flow exergy value can be negative if the pressure is below than the atmospheric pressure. So it is require external energy sources. Okay. So this is the end of part 4, chapter 1. Hopefully you find it useful, and good luck with your study. Thank you.